Welcome, AP Statistics, to Chapter 10. This is all about understanding randomness. Let's talk about the value of randomness and also the difficulty to attain true randomness. Per this quote from Robert R. Covey, I think that's how you say that, from Oak Ridge National Laboratory. Too important to be left to chance is randomness. Statistics relies heavily on things happening randomly. For just about everything else we are going to study this year, the assumption that outcomes are, or should be, generated randomly is implicit. The trouble is that people are not very random on their own, so we need to develop techniques to ensure randomness. Okay? People are not good at being random. And if you think people are good at being random, check this out. For example, if people are tasked with picking a, quote, random number 1 to 4, we'd guess that each number would have been picked about 25% of the time. Well, for whatever reason, the writers of our textbook asked people this question and did not get remotely 25% in each category. 3 was picked about 75% of the time. 1 was only picked about 5% of the time, and 2 and 3 were somewhere in the middle. So when someone is told to pick a random number, well, people are not very random. 75, 5, and a couple of different split is not random at all. That is laughably predictable. So this is one of many examples we could come up with for how people are not truly random. So how do we make randomness happen in statistics? So we can generate random numbers, and there are a couple ways of doing this. There's an old school way of doing this that I'll talk about, and there is a way that your calculator can do it as well. It's really neat. It's something called randint, random integer, also randint no rep, random integer no repeats. Two neat features on the calculator that we will discuss. So, like humans, technology cannot produce random results perfectly. They're a lot better than humans. Don't get me wrong. Tech is a lot better than humans in this category. However, it's not perfect. Random number generators on computers, calculators, and smartphones, like the one you probably have, rely on very complicated algorithms to compute random, quote, numbers. But since an algorithm is a pattern, the output can't truly be random. So calculators use algorithms to produce random numbers, or so we would think random numbers. They check out for humans, and humans aren't good at randomness anyway. But if you were to run the algorithm long enough, eventually it would repeat. So we call these generated values pseudo-random numbers. They seem random to us, but they aren't truly random. They are pseudo-random. But for our purposes, pseudo-random numbers will work just fine. So the algorithm is good enough. Pseudo-random numbers are about as good as truly random numbers, at least for our purposes. And the calculator, as you can see up here in this little picture, is equipped with such algorithms. You're also going to learn how to use a table of random numbers. That's the old school way of trying to do this whole business of randomness. You're going to get the experience of using a table of random numbers, and you're probably going to be very grateful for your calculator. Let's talk about simulations. Simulation, that's a technical term in statistics, and that's what we're going to talk about right here. So we know a deck of 52 cards, all right? Hopefully all of you are a little bit familiar with cards. Some of you are probably quite familiar with cards, playing fun card games as kids, even into your teens, I imagine. So we know in a deck of 52 cards, there are 4 aces, 12, quote, face cards. That's a jack, queen, and king. Ace is not a face card for our purposes. And 36 number cards, and that's all going to add up to 52. Remember, 1 is not a number card. It's 2 through 10, so there are 9 different number cards, 4 suits. That makes 36 number cards. So here's an interesting question. How many cards should you expect to draw before you have one of each type of card? That's an interesting question. How many should I expect to draw? In other words, on average, how many cards am I going to draw before I have one of each card? And of course, I'm not going to be replacing these cards. That could take a very long time. I'm going to discard them once I've seen them and once I have gone through the entire deck. Or at least up to card number, I guess it would be 49 at most. That would be a wild incident. But somewhere between 4 and 49 cards, I would get one of each card. Or rather, 3 and 49 cards, I would get one of each card. Because there are 3 types of cards: aces, faces, and number cards. All right, so here's one way we could solve this problem. We could shuffle our deck of cards, right? You want to shuffle. Again, randomness. Fun fact about shuffling a deck of cards: as long as your shuffle is good and you haven't just kind of whatever shuffled a deck of new cards that's always going to be in the same order anyway, if you truly shuffled a deck of cards and put effort into it, the order of your cards has probably never been replicated. And I'm saying very, very, very likely has never been replicated in human history. That's how many orders of cards there are, right? If you think about it, if you're familiar with the factorial notation, that's the exclamation point. The number of ways of organizing a deck of 52 cards is 52 factorial, okay? That's a really big number. That's a really big number. If you type in 52 exclamation point into your search browser may may have a little trouble with that one, or it'll give you an error of some kind, meaning there's a lot of places, decimal places we're not including because this number is so big. So if you truly shuffle a deck of cards, there's probably been no deck of cards in history, all shuffles of all decks, that have ever been like your deck of cards. So you're holding something very unique if you do that. All right, I got to stop being sentimental. Here we go. So shuffle the deck of cards. Keep drawing cards until you have one of each. Okay, so we're going to keep drawing cards, discarding once we're done with each card, or else this could take a long time. And once you get one of each type of card, record how many cards you have drawn. Okay, and that will be our outcome that we're looking for. How many cards do you need to draw before you get at least one ace, one face, and one number? And then we complete the process many times. One time will give you how many cards it took to get one of each type of card once. That's not very helpful in determining how many on average we can expect to pull. It would be much better to do, really be essential, to do this process many times, to run the simulation many, many, many times over, and eventually you'll start to see a pattern. And the structure of that pattern will appear rather familiar, and I'm not going to spoil it for you, but if you were to conduct many simulations and say, okay, in this simulation, I was able to pick the 3 types of cards in 10 pulls from the deck, and the next time 12, and the next time 7. Ooh, I got lucky that time. And the next time 16. Oh, not so lucky. If you were to do that many, many times, the way those outcomes would stack up is rather fascinating, and you have seen that shape of a distribution before many, many, many times. But I'm not going to spoil it for you. All right? So, suppose we don't have cards. Bummer. Actually, that makes our life easier. If we had cards, we might want to use them, but actually we shouldn't use them. There are much easier ways of solving this problem than actually picking from a deck of cards. We can still solve the problem using a simulation, and here's where we get into simulating this process. That is a model of a real-world situation using random outcomes to mimic the uncertainty for a variable of interest. The variable being how many times you need to pull from the deck to get one of each type of card. All right, so we're going to simulate this whole process, and yeah, I'll show you how to do it in 2 different ways, and I'm sure you'll have a favorite after I show you these 2 ways. All right, here we go. Let's talk about simulations. So we talked about this whole card thing. That's the real deal, but now we're going to simulate this card pulling endeavor of ours. So simulations can be tactile or abstract. Tactile just means you would pull cards or pull little slips of paper out of a hat that have names of cards. That's tactile, all right? Or abstract, and we like abstract, especially if we have a graphing calculator or some statistics software on hand. All right. Formal statisticians prefer the latter. All right. And we like to be as formal as possible, even at this stage of the game. We can solve this problem using numbers only. How do we do that? Well, here we go. Our simulation component, that's a technical term. There are several technical terms on this page. Take some good notes if you haven't done so already. So our simulation component, that is a single iteration of the situation being simulated, is picking a card from the deck, all right? So the component of our simulation is picking a card, okay? So that's our process we're going to do in our simulation. So we can classify each possible component outcome, all right? So another technical term, component outcome, that is the result from an iteration of the situation being simulated, and oftentimes we just call this the outcome, all right? So you have the simulation component, what are you doing? Now we have the component outcome, or just the outcome. And there are several possible outcomes. Aces are, we could say 0, 1 through 0, 4. We're using 2-digit numbers. So we would interpret 0, 1, 0, 2, 0, 3, and 0, 4 as my 4 aces. Which aces are they? It doesn't matter. So we're using 2 digits for each possible card. We need to label 52 cards. 52 is, of course, a 2-digit number. So we'll use 0, 1, and 0, 4. Face cards are 0, 5 through 16. There are 12 of them, and if we count card number 5 and card number 16, we see that there are 12 values there. And number cards would then be 17 through the last card, number 52. There are 36 such cards. So in the simulation, we combine a sequence of outcomes into an event that we pretend takes place, all right? So we run the component over and over again, pick our card, and we get a bunch of outcomes, all right? And that outcome leads up to some event, all right? And that event that takes place is called a trial, all right? So one trial would constitute picking as many cards as we need to pick before we get one of each type of card, all right? In this case, each time we figure out how many cards we need to pick to get one of each type constitutes a trial. So we pick a card, we run our simulation component, we look at the outcome, and then we pick another card and look at that outcome, pick another card, look at that outcome, and once we've finally gotten one of each card, we have completed one trial of our simulation. And then we have the response variable. This is the real hero of the story. The response variable is the result that we record at the end of each trial, right? So we run our simulation component, look at the outcome, run the simulation component, look at the outcome, run the simulation component, look at the outcome. And then once we've completed a trial, at the end of the trial, we have our big result, all right? And that big outcome, that big result is the response variable. All right, the response variable is the result we record at the end of the trial. The response variable is the number of cards chosen until we have at least one of each type of card. All right, and the use of the phrase response variable is very intentional. We've seen that terminology before. If this is the whole explanatory process, if you will, and what we get in response is what we record. And the variable is, well, how many cards do we have to choose until we have one of each type of card? And that response variable can assume values from 3, we got really lucky, to 49. We've picked everything except an ace. So after many, many, many trials, we can better understand the nature of that response variable. Here's what a simulation looks like. We start with our different components. And each of those components lead to an outcome. After we've recorded many outcomes and run the simulation many times, we have a trial. And after we get a trial, we now can record a value for our response variable. So putting our familiar scenario to it, you pick a card and you get different outcomes. And this is a really lucky set of pulls. We've chosen one of each type of card by literally the fourth card. We have thus completed a trial, and our response variable would yield 4. There are 4 cards it takes to pick one of each kind of card. So here's a formal description of how a simulation works. This is the extent of the description you would need for the homework, as well as for a free response question on the AP test. So we're going to first identify the simulation component. You don't need to write the part that's bolded. You do need to write the part beneath it. Our component is picking a card from a standard deck of 52 playing cards. Number 2, specify how we will model the component's outcome. The digits 1 to 52 are equally likely to occur. One possible alignment would be 1 to 4 is an ace, 5 to 16 is a face card, 17 to 52 is a number card, and we would ignore 00 as well as 53 to 99. Right? If we see those appear, if we're using a table of random digits, and you'll see how those could appear in just a moment, we would just ignore those values. Then we explain how we would combine the components into a trial. So we pretend to pick cards, figuratively, repeat components until we have one of each type of card. We do this by looking at each random digit and seeing which type of card it represents. We continue until we have obtained at least one of each type of card. All right, so that's how a trial works. Then we need to clearly state what the response variable is. We need to state the true hero of our story, which is the number of cards chosen until we have at least one of each type of card. Once we have given a formal description, then we can run trials and gather results. We can either use a table of random digits. There's one at the back of your textbook. I'm going to use ones on the next slide. You're welcome to use either for the first trial, and then I'm going to show you how to use the calculator for the rest. So I do want you to see how to use a table of random digits. This is the old school way. Then I'll show you how to use a calculator to model a trial for this simulation. All right, so this is a table of random numbers. These numbers, there were back in the day, this is a long time ago, statisticians had a bunch of books sitting around that just had tables of random numbers in them. And the reason they had these tables of random numbers is so that they could do simulations like this. All right. If they didn't have cards on hand, they wanted to do things efficiently as you could in those days, you would just crack open a table of random numbers, just kind of spewed all over the place, and you would do a simulation using those random numbers. Now, how they made those numbers as random as they were, I'm actually not sure. Humans are not good at randomness. I'm not sure how these were generated, but they were helpful for statisticians. Okay. So here we go. Here's a table of random digits. Let's get to work. The first 2 numbers we see are 5, 7. So 57, that's not a card. So we're just going to put a dash here to say, yeah, that's not a card. Now, 45, that's a number, okay? So we've counted one actual card so far. The dash doesn't count for anything. We've only counted one card so far. Our next is going to be 57. Oh, that's not a card. And then we have 24. Ooh, that's another number card. Okay. Then we have 55. Oh, not a card. Then we have 93. Definitely not a card. 94. No. 90. 30. Now we're on to something. And then we would just keep going and going and going. 17. Yeah, that's a number. 33. That's a number. 46. That's a number. And 35. That is a number. And we would keep going on and on and on and on. And I'm just going to go all the way down here. There was another 35 that appeared. And so we need to make sure that we don't count that 35 because we had a 35 somewhere up here. That's why I put the dash and then the repeat. We got a 35 again. But all of a sudden we see down here we have an ace. There we go. We have all three types of cards at this point. So how many cards did I pick, quote unquote? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So our response variable, number of cards it takes to pick one of each type, would be 14 cards. Yeah, I never want to do that again. And I don't think you do either. So I'm going to show you how to do this on the calculator. Here's the basics on how to run a simulation with a graphing calculator. So on your calculator, you're going to go to Math, and then you're going to hit the button that says Prob. That's probability. Then you can use randint or randint no rep, both of which have 3 arguments, and an argument is just one of the things you enter. So to generate a certain number of outcomes, you would use randint, and then you'd need to enter a lower boundary, an upper boundary, and some number of outcomes. Now, note, randint will repeat values, okay? So that's why you have to specify a certain number of outcomes, because if values can repeat, then the values can go on forever and ever. And the calculator doesn't have time for that. So you need to specify a number of outcomes. So if you don't enter a number of outcomes, you will just have one outcome appear at a time, all right? To generate one outcome at a time, leave the last argument blank and just keep entering randint, lower bound, upper bound. And again, your outcomes may repeat. But if you don't want the outcomes to repeat, which is what we want for our problem, we would use randint no rep, okay? And that's what we want for our problem here. You would enter lower bound, upper bound, and you can enter number of outcomes, but that is only for the TI-84 plus C and newer, okay? So for your older calculators, for randint no rep, you would just enter a lower bound and an upper bound, and what it would do is list out all of the values in the interval you specify in a random order. Okay, so we're going to run this simulation on the calculator and see how we do. As I said, for this one, we're going to need randint no rep. So I'm going to go to Math. I'm going to go to Probability. And I'm going to go all the way to the bottom, and I see randint no rep. So your interface may be a little different, but you'll have at least 2 arguments. For the lower boundary, I'm going to hit 1. And then for the upper boundary, put a comma in between, I'm going to hit 52. Okay, so this is going to sort through all of my cards in a random order. This is like shuffling the deck and picking, all right? So I'm going to hit enter, and here is my random order. So let's see what we got. 30, that is a number card. All right, so we already have our number card. Very good. And second, we have 14. That is going to be a face card. All right, 17 is a number card. 48 is a number card. And we have 2. That's our ace. Very good. So suppose we needed more than 5 cards. We got a nice pull there. We would just keep going to the right, see more and more and more and more and more and more values. If you want to shuffle the deck again, you just hit enter and enter again and enter again, and you can just keep shuffling the deck over and over and over again. Isn't this so much better than a table of random values? I think so. So we ran the simulation, stacked some components together into a trial, and our response variable output 5. So I actually ended up running 20 trials, and this is the histogram of the values for my response variable. This one is definitely an outlier. It took me 30 different outcomes to complete this trial right here. So my response variable value was 30 for that one. That was kind of crazy. It was getting annoying by the end of that trial, but most of the trials ended very quickly and things do taper off. So the distribution appears to be right skew. And I imagine that trend would continue if I were to increase the number of trials.